So, hello everyone. My name is Thiago Alves, and today I will talk about honeybee conservation with Python. So, I'm now a student of computer science in Brazil, and also I'm doing my master degree in IPB in Portugal. So, when I was called in the last year to start my master degree in Portugal, at the time I was working with artificial intelligence to games, like that paper of the DeepMind to play Atari. But it was necessary that I changed my topic to start my master degree when I came to Portugal. And the topic that they gave to me was to work with bees, something that I've never thought that I would work. But they explained to me what would be necessary to me to do to my thesis. And they explained me the problem that they had. The problem was that usually when a beekeeper or a researcher in the area of apidologie area, they have some tasks, and to do these tasks, they need that many times during the year, they need to count and classify the content of each cell in the bee frames. And this is usually is done by hand, and it's a big problem for them. So they proposed to me to make to develop an automatic way to solve this. And the solution proposed was to use deep learning to solve this problem using image and also using image processing. So this was the job that was given to me. So these are examples of the cells that I needed to classify and count. For example, the eggs, larvae, and pupa that are cells from brood, empty cells also, and the food cells. They usually need to do this task many times during the year to see how the bees are, how the hives are, if they, for example, if the hives are good with a lot of food, they can see this counting the content of the cells. And if they have a lot of food, so it means that the hives are in a good health. So because of this, they needed to do this during the year. I needed to talk it first. So knowing the data set that they give it to me, to create the data set, they used a tunnel like this, and they took over 2,000 photos of the frames, like this one in the images. And this was the image that I would work on it, or it would work on. And also, they had a help of a beekeeper. He by hand, he labeled over 70,000 cells to use it in the training. So this task took him over 3 months. So he really did hard work to have this data set. And after, we started to working when I came to Portugal. The first thing that we thought that would be necessary would be to reduce the problem, because the images were big, like 6,000 by 4,000. So we needed to use some way to make the segmentation of this only the cells part, the cells area. So the first strategy that we have was to work with OpenCV and try in some way to change the color spaces and see how it would work if we could in some way to filter the colors and remove the background. But as can be seen in this image, a lot of the parts of the frame couldn't be removed only by filtering the color space. In this example, we used the HSV color space and we tried to put in some ranges the colors, but this approach didn't work. So we tried another one. The next approach that we thought that would be a good one would be let's try the Hough Transform. The Hough Transform is one method. It is implemented on the OpenCV. And with it, we can detect, for example, different shapes in an image. For example, in this case, we try to detect lines, and in some way to try to only segment the center of the frame. But it worked in a lot of times, but not in all of them. And in some cases, we had some, for example, in this frame, a rat bited the frame. So if we use one strategy like that, we could have a lot of false positives inside these areas. Also, not all the frames were the same height, so we couldn't use this strategy to all of them. So we needed another approach. But after I will talk more about the other approach, because at this time we stopped a bit from trying to make the segmentation, and we tried to detect the cells. Our first approach was, let's try the Hough Transform, but to detect circles in the image. And it worked in some way, but as you can see, we couldn't detect all the cells in the image. Maybe because of some filter that would be necessary, or I don't know, it wasn't working at that time. So we thought, maybe we can get some of these detections, the best detection. We thought to create that we could create some markers like these ones, where we get on center and we detect what is the six next cells. And with it, we created some markers. And we thought that with these markers, we could, in some way, to make the prediction of the cells in the side. But because of the distortion of the lens and the way that the bees creates these frames, we couldn't do that to make the prediction. So we needed another approach. So this approach we tried to do using a Voronoi diagram that is implemented in the Shapely. But at this time, this approach didn't work. But the idea was good. But I wish that it would work. The next step, we thought, well, we need to step back and analyze the problem again. So we had two problems. The first one was it has so much noise in the image. So it was a difficulty to make the detection of the cells. The second problem that we had was the way that the bees creates the bees work, because they start from the center and go to the borders. So in many images we had this problem where the center was darker than the borders. And if we tried some way to use a histogram normalization, we had a problem, because the center would get darker and the corners would get brighter and brighter. So with trying a lot of different approaches and a lot of different filters, we achieved this goal. That was to use histogram normalization called Caffe, but this normalization works in a different way, because instead of get the entire image, it gets small pieces of the image, and in each one of these pieces, it applies normalization and a contrast. So with it, we could get an image like this, and we still had the problem of the noise. So to remove the noise, we used a bilateral filter. The bilateral filter has a different way of working compared to the average filter or a Gaussian filter. Usually when you use a Gaussian filter or an average filter, you lose the edges of, for example, the edges of the cells, and you get a blurred image. So if you use a bilateral filter, you can remove the noise and still maintain the cell's border. that was necessary to make the prediction of the detection of each one of the cells. And in this time, the Hough Transform worked, but not at the first attempt. We created a script and we tried a lot of hyperparameters of the Hough Transform, and with it we could achieve the one result like that, where all of the cells were detected in the image. So the next step was to make the classification of each one of the cells. For this, we used the NVIDIA digits. The NVIDIA digits is a web software, web-based, and with it we could train a lot of different models only using a visual way. But this software used the Caffe as a backend. It also used the Torch and the TensorFlow, but we used the Caffe backend. And it's important to say that this software is available in the GitHub, and it is written in Python, and also it's open source. So we used this platform to make the training. And the first results that we get was from the training using the AlexNet architecture. We trained this architecture from zero, so from scratch. So we didn't have the weights already trained in another dataset. So we trained from scratch, and we used the input images, only the content inside of the cell. That is 48 by 48, an image 48 by 48. With this, we get the results as 95% of accuracy in the validation set and 92% in the test set. But we have a problem. That was, looking to the confusion matrix, we saw that we used the scikit-learn confusion matrix, and looking at it, we saw that using only the center of the cells, the capped cells, the brood capped cells, and the cells with honey, there had a lot of confusion in these detections. So maybe we needed to use a bigger image. Another problem that we had was that the annotations made by the human, the beekeeper, were more perfect than the detections. So they were slightly different in different ways, in different parts of the image. For example, here where it's difficult to see where is the cell, so the detections usually is different from the annotations made by the human. So to solve these two problems, we thought, let's try a lot of different models, with a lot of different input sizes, and in some models we train using the detections made by our detector, and in other models we try with the annotations made by the beekeeper. So that's what we did. We created around 40 different models to try a lot of different sizes, and for it we used the API provided for the NVIDIA digits, and we created a script to run all of it and get the models after the finish of the training, and pass to the test set and see which model was the best. So as a result, we discovered some relations. For example, the input size of the image impacts in the accuracy with high confidence. As you can see, as bigger is the input image, bigger is the accuracy in almost all the cases. After some size, it starts to decay. But it was a good point that we discovered. It was interesting because we learned that the neural network learns that the center is really important to the prediction, but it still uses the content from the around the center to make the prediction. So we saw these results, And we thought, maybe that problem that we had in the beginning, we could solve using a classifier, where we make some annotations with the false positive detections we put in one class, and the another class, that is the cells predicted inside the frame, we put it in another class. And let's try to create a classifier with these two classes. So we created this data set and used a Google Net network architecture, the architecture inception, to make this training. And we got some good results with it. We can see that even in those cases where we couldn't solve with our last approaches, we could solve with this one. So the results were really good. But to process all the cells with the one neural network, only to make the segmentation in this way, and after use another network to classify the content of each one, would be a process that would use a lot of processing. So we needed maybe another strategy. And in that time, we were working in a study group that we have in my university. And the content that we was discussing in that time was a Kaggle competition. And this competition was necessary to make the segmentation of cells. Yeah, in a lot of the solutions, they were proposing to use encoder-decoder networks. For example, this is a UNet, one architecture, where you can put in one side one cell and expect the segmentation in the other side. And we thought, maybe we can use the same strategy, but we can put in one side some small pieces of the image and expect that the neural network learns to make the prediction of only the area where is the comb, where it really is the comb. So we created a data set to do it, and with the Photoshop, we selected I think that was 60 images. We selected only the content inside, and we created a data set with tiles like those. And these tiles were 128 by 128. And this was the data set that we created to try to solve this problem in a more efficient way. So we created this model based on the UNet, using the carrots and the TensorFlow. And as can be seen in the loss, the model really learned to do this task. Here we have some examples from the input, the prediction with some confidence areas, and after applied the one threshold, the result is quite similar to the ground truth that we was expecting. And after we process all those tiles, we rebuild the image using some stacking of the NumPy, and we could achieve these results. And it can be seen that we solved in a good way that problem of only the segmentation of the comb area. So the using of this network really solved our problem. So. And also can be seen that in this image, for example, that is an image that was took using a smartphone camera without that tunnel to have a controlled light. Even in this case, it was possible to make the segmentation of the frame and the detection of the cells using the approach that we developed. Also, this is our final results, where in the first image is the annotations made by a human, these first images. The second one is the prediction made by our model. And the third one is the difference from the annotation and the prediction. To achieve these results, we used a neural network, Google Net also, but with the weights pre-trained the weights were pre-trained in a previous competition of ImageNet, that is a competition of image classification. So we used those weights to train our classifier. And we could achieve over 93% of accuracy in these images. In a final set that is not the set that was labeled by the beekeeper. So this is our project. In the next month, I believe that in 3 months we will finish it and we will open source all of it to, if anyone wants to contribute or just use our solution. And some acknowledgements from the people that really helped us. And that's it. Thanks. The solution will be in this GitHub.
We considered using the unit for everything, because actually you can have multiple classes, right? So it could segment the whole image for each cell, right?
And also the content of the cells. Yes, this is one approach that we are think that can be possible to solve, but we didn't solve it yet, using it yet. We tried using the VGG net, but in that case we didn't have a really good results. But probably using the UNet to make the segmentation and the classification using the instance classification, we could achieve this result that you said. But I believe that we will still try this approach. And I believe that is a good one, because we could only measure the error of each one of the predictions, the segmentation predictions, and in some way to predict the number of the cells that would have in the predicted class. So yes, it's a good approach, and I hope that we will try it in the future.